Yeah, I'm founder of 3MDEP, working in platform security technologies since 2008, and mostly working with open source firmware and trusted computing technologies. I'm in boards of directors of Open Security Training Tool, which is like very nice Zeno Kovac platform. I'm also in steering community of Trenchboot project, which is open source implementation of dynamic root of trust for measurement, but maybe we will get to root of trust also in this FAQ a little bit. Yeah, conference speaker and open source advocate. Regarding how it would look like, I have like a bunch of questions prepared. I would be glad to take as much as possible questions from you, of course, at the point when I will end up with my set. And yeah, and that's how we will operate. So let's start with something very, very basic. What is UEFI Secure Boot? And of course, depending on level of nitpickiness, we can say in simple words, we can cut in corners and we can simplify that this is just the API in the UEFI specification. And regarding the implementation, it is API, reference API implementation in something called Tiano Core EDK2, which is UEFI specification reference implementation in C with BSD license available on GitHub. To answer this question, UEFI Secure Boot is an API which provides infrastructure for UEFI image load time authentication. What does it mean? It means when we're trying to run our bootloader, our GPU option ROM, our network card firmware inside our BIOS, or we try to just run some grab or Windows bootloader, or simply maybe application that will test our memory like memtest, the UEFI interface will verify during the loading if the signatures for the given image are valid and according to the certain policy set up in the BIOS. Yeah, so this is mostly what UEFI Secure Boot does, and there are a lot of nitty-gritty details related to that. And yeah, and this is what about this whole training, this FAQ, and then the training on hardwear.io is. So where you get the information about UEFI Secure Boot? What's the authoritative source of information about it? Of course, UEFI specification, but the best write-ups typically about UEFI Secure Boot often can be found on Microsoft because Microsoft essentially driving the development of UEFI specification, and also because Microsoft become the holder of the signing case for our bootloaders, and also is responsible for managing all the CVEs which are related to bypassing Secure Boot in bootloaders. That's why Microsoft publish a lot of documentation how to, with the best practices, develop and integrate UEFI Secure Boot, and how to introduce signing process for the bootloaders, for the drivers also, because they also allow to sign option ROMs. So yeah, quite a lot of interesting documentation can be found behind UEFI.org, and also learn Microsoft.com, and those are the links you have here. Those are often explained. Finally, the goal is that finally the goal of this documentation and goal of using this information which are behind this authoritative source is to essentially enable hardware makers and also people who deliver the components like BIOS or drivers to make those work correctly in UEFI Secure Boot, with UEFI Secure Boot across whole ecosystem. So when you're buying your new laptop, when you're buying your server, or you're buying any other hardware, you are sure that if you connect your new graphic card, everything will boot and it will not stack because of not signed option ROM. It also, when you're trying to install your favorite operating system, which can be something different than Microsoft Windows, it will still boot. And that's what those sources, that's what those specifications try to describe. And of course, the problem is that sometimes the specification do not follow the implementation. So specification is way ahead of the implementation. So you have to make sure that to understand with what version of the specification and what version of the documentation you are really complying to. And of course, Microsoft got requirements for that. If your hardware is Windows Logo certified, then you have to meet certain version of UEFI specification. This is 2.7.1, if I recall correctly, but the details can be also found in Microsoft source. Okay. What are the ways for end user to deal with UEFI Secure Boot? Yeah, so of course, like first is just a joke. It's like we do not recommend disabling UEFI Secure Boot, but this is one of the option, this is terrifying how often it is recommended to disable UEFI Secure Boot to perform some operation. So we very often can find in some resources in internet that, okay, if you want to install this operating system, sometimes even secure operating system, you have to disable Secure Boot. Or to use this or that, you have to disable Secure Boot. Of course, this is very bad, and it's just proving that the ecosystem is not mature, and that the knowledge about how to comply with the requirements needed in the ecosystem, needed by Microsoft for signing, needed by UEFI Secure Boot, Secure Boot and UEFI specification is just not there yet, and that's why the education for that is very important. Unfortunately, we have increased number of various infections, problems, exploitation of our boot chain, and we sometimes wondering how we should deal with that. So the second option is we essentially using pre-signed images for our favorite operating system vendor, and of course we have to pay for all the sins that this vendor did. So, for example, we have quite a lot of CVEs recently, which Pixie fail, we have PK fail, we have boot hole. This was maybe a little bit older. We got Black Lotus. So all those issues were not because of the malfunction of UEFI Secure Boot mechanism per se, but rather by either wrong implementation, either wrong key management, either misunderstanding about whole ecosystem and who's got which role in this ecosystem. So, and the third option, so this pre-signed images are our second option, and the third option is essentially to use your own keys, to essentially own your boot process, sign everything yourself. Of course, this option is not for everyone, but in my opinion, this is the only sensible option, and that's what I also always promoting, because holding your own keys, signing, and making sure that that your boot chain is not compromised is the key point of having UEFI Secure Boot. So of course there is this machine owner key concept in the Linux ecosystem where you're using shim and you essentially provision your own key to verify Linux kernel. But of course, in this case, shim, which is used as a thin layer between Linux and BIOS, have to be signed by Microsoft. And this is not always easy. Not every distribution, Linux distribution, can afford that. So this is not for everyone. So machine owner key is one of the options I described in the training in more details. Yeah, because of the tooling, because of the various reasons, it's not always the best one. Also, the process for shim signing is not that easy. So not every distribution can afford to get through that process. And then this process, mostly maintained and enforced by Microsoft, became more and more complex with every new vulnerability, because they put another rule, more and more rules to make you being approved by them to be signed with Microsoft keys, and then to be able to use your bootloader or use your drivers on every possible hardware which is out there. Yeah, so third part is the hardest part, but I think it is the most rewarding one. And I really recommend you to educate yourself and hold your own chain of trust and hold your own keys for your boot process. And yeah, that's not for everyone, but everyone who's technically capable. And I guess that the goal of our goal of technical experts is to simplify this process and make it as most available to everyone as possible. Okay, this was a little bit about what we can do. Then maybe a little bit about what version of specification which we should use. This is complex question because, as I mentioned, the UEFI specification lifecycle is not that simple. Essentially, to get from the specification level to implementation, the road is very, very long. So there is long time between the new specification being really published and then whole reference code updated. So because first we have specification publication, then we have reference code update. So Tiano Core EDK2 BIOS reference code is updated. Then independent BIOS vendors can pick that reference code and use it to build their own BIOS, or some option ROM vendors or hardware vendors can use that to build their own option ROMs. And then, of course, we have to go through compliance, testing, and so on and so on. And sometimes it's taking years to get from the specification level number to compliant driver or to compliant BIOS. So that's why we're not using the most recent one, and it doesn't make sense to use the most recent one because essentially it's not practical, it's not existent, you're not getting it in the ecosystem on your hardware. So you have to use a little bit older, maybe the one which is more kind of more popular, introduce it in more implementations. And looking at what's going on right now, we can say that that version 2.7 is probably one of the most popular. It already has a couple years, but yeah, it's already probably 5-6 years or something. So other methods. So then you have also, of course, when you're running core BIOS, then you would like to know, okay, what version I'm running, with what UEFI specification version I'm compliant to. It's not easy thing. There are no tests for that to confirm that. And why you would like to know that? You would like to know that because if there are any vulnerabilities in the previous implementations and spec introduced fixes for that, then you would like to know, okay, how far I am from the version, what I have to do, how much I have to update to get through the version that is vulnerable. Okay, and some BIOS vendors are very kind and present information about the version compliance on your main page of the BIOS. So that's very good. Of course, we have to trust that they really tested and verified that this compliance is there, because there is no like an external authority which will confirm that. And as far as I know, the publicly available compliance tests are a little bit outdated and really do not confirm the most recent version. Yeah. So what are the other options? So other options is to verify what versions you have. You essentially build the BIOS yourself. Many things it's very hard, but it's, if you really look into that, this may happen to not be so complex. And part of the training is also to showing you that this is really simple, at least for the devices which are supported. Okay, so foundation of the UEFI Secure Boot are UEFI variables. There is a training publicly available on UEFI variables, which like extensively discuss that on OST2. But anyway, the point here is that basic information about UEFI variables is required to understand how UEFI Secure Boot works. There are a bunch of variables: platform key, key exchange key. There are variables like DB, DBA, DBX, DBT, DBR. So all those variables, sometimes those DB are called databases, but really those are variables which you extend, adding additional information. So those variables are just key value pairs, where the key is just identifying information. It is typically name plus GUID. And the attributes essentially are used for making a UEFI variable an authenticated variable, so it can be updated or it can be updated only by the holder of the private key. There are also other variables, but the one for the UEFI Secure Boot are those authenticated one. Okay, and the goal of variables is of course keeping some user configuration, and then we can use it for boot order. But most important use case is for UEFI Secure Boot, and those variables, we're playing a lot with those variables because those variables also, determine the UEFI boot policy and what to do when the criteria for the authentication of the loaded UEFI image, so loaded driver or loaded bootloader, will be not met. What will happen in this situation? And this depends on the state in which a UEFI Secure Boot is, and this state is also determined by those variables. So there are possible states like setup mode, there is deployed mode, there is audit mode, and there is user mode. And with switching through those 4 modes using various values in UEFI variables, and that's also part of the training. Okay, what UEFI variables protection mechanism? So you may say, okay, so there are those variables which are foundation for UEFI Secure Boot, but then okay, how those are protected? The specification says responsibility to the platform. So essentially platform firmware or platform components which are there, because it really depends if we're playing with laptop, with server, depending on our target, various possibilities from protecting the variables we have. But one thing which is very important to understand is that UEFI variables are not considered confidential. So, and we should not use those for confidential information. We can, and there are ways for doing that, but essentially this is not the main purpose. So no confidentiality. The most important thing about the UEFI variables is that integrity and availability have to be ensured, because of course if we have some variables which, for example, keep our platform owner key, so the most important key in UEFI Secure Boot, then we don't want it to be replaced by malicious actor. Yeah, so we want to make sure that some integrity is there. Of course, how those properties are provided is very platform dependent, but there are some good practices to follow. Yeah. So, for example, and then in these good practices, we can divide the methods for protecting between software, like protecting against software attacks and protecting against hardware attacks. For software attacks, we have things like variable lock. So this is essentially a mechanism introduced in EDK2, where after a certain phase of the boot process, you cannot modify given variable from the software. There is also variable sanity check. So this is essentially a mechanism which help you make sure that if someone will change the variable, it will not be changed to the unexpected value, so or a value not allowed. So it's essentially some kind of validation before setting. Yeah. So those are software checks. And there were also implementation which of course did the confidentiality thing using, for example, even some external Krypton engine to encrypt variables. That's one way of doing things. Yeah, so other way is some vendors use special format of UEFI variables. There are also like hardware protection mechanism where there is this reply protected memory block. If storage supports that, if UEFI like BIOS storage or UEFI variable storage support that, then you can pair the properties of the storage, like a reply protected memory block, and trusted execution environment, which can be, for example, management engine, and then those two can talk with each other to check if really the variable which is stored on the chip is valid. Of course, then this variable is encrypted thanks to the key exchange between the storage and the trusted execution environment. So if you're even trying to do something from external, then it will be detected and it will quickly either roll back to the default values or essentially will stop booting. So that's some way of doing things. Of course, there are more software side protection mechanism, but yeah, I don't have time here to talk about all of them. And to be honest, this is not the most important thing, because it really depends on the things that given platform provide. So UEFI specification mostly care about the interface that operating system and BIOS have for changing the variables and managing the variables, and it cares less about how hardware should protect it, or what are the other advanced implemented features or advanced features in implementation to protect against software attacks. Okay. What is root of trust? This is also like, this could very quickly go scientific, but I don't want to be very like a TCG, Trusted Computing Group nomenclature precise, because they have very good definitions, very like kind of scientific level definitions. But after sitting in this ecosystem, doing root of trust assessment, provisioning, and maintenance, I think that definition that's saying that root of trust is an entity in the system which is unconditionally trusted, is this definition is good enough for most of the discussion. And why it is unconditionally trusted? Because there is no other external entity which could validate it before, because then that entity would be root of trust. And of course, then we can ask ourselves, okay, why we're talking about root of trust when we're talking about UEFI Secure Boot? So UEFI Secure Boot, many people think this is really the root of trust technology, and this is most important security technology for platforms booting. And this is not exactly true. UEFI Secure Boot is chain of trust technology. It relies on some previously established trust, transitive trust in the platform. So essentially, UEFI Secure Boot is only available at the last stage of the boot process for platforms. And of course, because it is exposed to operating system, we know about it. We heard about it in media, and we heard way less about the root of trust technologies like Intel Boot Guard or AMD Secure Boot. We heard way less about those ones. But those are needed to make sure that the security of UEFI Secure Boot and the chain of trust it delivers will be ensured. Yeah, I guess that's about root of trust. So maybe we can also ask ourselves, okay, how typically root of trust is implemented in modern platform? And typically it is like two things. It's a hardware and code. And typically there is like a small code running in trusted execution environment, like a management engine or AMD secure processor, or this could be trust zone, or could be other small processor, which typically runs before main CPU is released for running BIOS or whatever bootstrap firmware you're using. And that small code is responsible for maintaining the life cycle of the either of the technology of immutable of keeping the key, immutable technology for keeping the key, which is then used for verifying that the next stage of booting is authenticated, is genuine, and coming from someone who holds the private key. So that technology is typically relying on if-uses or one-time programmable registers. Recently, also physical unclonable functions are used for that, or helping in establishing this hardware root of trust. But of course, there is some life cycle which is needed. So before fusing, after fusing, and then maybe if we have possibility to transfer ownership, then we can have code which just maintain that life cycle longer. So for example, we have some fuses populated with, let's say, my key, but I want to sell this hardware to someone else. So I could transfer this ownership, and some platforms allow that and some platforms do not allow that. And it depends really on how root of trust technology is deployed and how it is constructed, how it is structured. Okay, so there are like two main, let's say, words of root of trust. In this case, root of trust for measurement. So root of trust for measurement is essentially it's related with TPMs. So in PCR0 of TPM, in the first register which keeps the measurements, we typically store initial measurement of the first code running on the main CPU. Of course, this is like simplified view because I don't have time to go in way more details here, but essentially we have static root of trust for measurement, which essentially happen at the beginning of the boot process of the platform. So at the beginning, at given static point in time of the platform lifecycle, typically at the boot. So in case of Intel Boot Guard, which is one of the technology that I discussed as a part of hardwear.io training, we have first measurement stored in PCR0 by Intel Boot Guard technology, and that PCR0 is populated with the hash of the beginning of the BIOS. So before even CPU starts to execute that. Okay, this is fine, this is good, but SRTM has one problem. To re-establish trust in platform, in platform firmware, to re-establish this measurement and make sure it's really good, we have to reboot the platform because it's happened at the beginning. So some platforms cannot be rebooted easily. So there is this small problem that was it lead to creation of dynamic root of trust for measurement. So concept of dynamic root of trust for measurement is a special instruction in the CPU, or there can be other implementation because ARM does this little bit different. But anyway, let's hook into the AMD and Intel, where there is this special instruction. When you invoke this instruction, you essentially enter special mode, and in this mode you can re-establish trust into the platform, because you essentially creating, you can say, some small enclave, but this is not like SGX enclave. It is concept which is much more older than SGX. So protected area of the memory is created in which you put some piece of software, and it's protected against, it should be protected against SMM attacks, against DMA attacks. And that piece of memory is automatically by hardware measured into TPM, into PCRs 17 to 22. And those measurements are stored. Then you can verify that this dynamic root of trust of measurement really happened. And that small piece of code which was measured essentially re-establish trust into your platform, because it's measured at beginning of new execution. And from that point, you can, for example, verify if all other software running on the platform is intact. Of course, it is much more complex in practice, but in theory, it looks like that. There are even patches, I guess 13th or 14th version of patches to Linux kernel, which is done by Oracle. It's done by Apparatus Consulting and 3MDev, company I'm founder of. So I hope this technology will be more and more popular soon, despite being already quite old. What are the real-life examples of root of trust? I already mentioned. We have this Intel Boot Guard from Intel. We have AMD platform Secure Boot, which is not very popular because there was this very interesting article from Serve the Home, where they put the processor into mainboard and it was fused by the first boot, and essentially then you couldn't move the processor to another mainboard. It was the design is like very questionable. But there are other interesting methods and very popular methods of server root of trust, establishing root of trust on servers. One method is through OpenBMC, and we essentially have OpenBMC, which or platform firmware resiliency chip, which is similar to OpenBMC. And in that case, we can verify everything. This chip verifies everything before allowing main processor to run anything. On ARM, we typically deal with something implemented in boot ROM. and then we essentially fuse some OTP registers with public key, as I said before, and then bootrom, when it sees, okay, there are some keys there fused, so I know that next stage that I will pass control to, I have to verify its hash and check the signature, and only if everything is okay, I will allow to continue. Yeah, so this is typical implementation for. There is very interesting also implementation for power. There is also very interesting implementation. I guess most of the RISC-V getting that. But if we really want to dive into root of trust area, then we should look at OpenTitan and Calyptra, because those are open hardware up to the silicon. You can check the gates. You can even create your own chips. Of course, you need quite a lot of money for that, but still everything is there, code is there, and even reading the specification gives a lot of knowledge what's the current state of the art implementation for root of trust. Okay, yeah, so this is a question that I would like to thank Diego Porras. I hope I spelled his surname correctly. He asked this question on LinkedIn while I was promoting this webinar. So he asked, how can you start learning and experimenting with UEFI programming without working for an OEM? So he was kind of saying, okay, but I have those platforms, but this BIOS is closed source. I cannot play with this. So how I will learn UEFI Secure Boot if I cannot change anything because everything is proprietary? So yeah, there are at least 3 ways for doing that. I'm pretty sure there are more, but those three I'm using during the training. So first of all, you can use emulated or simulated environment. So first one is QEMU, is like a basic tool everyone knows and is very helpful in running some BIOS and then learning, okay, how it works, what it does behind the scene. The second one is CMix. Intel CMix is a simulation environment. I would say in the details of how processor working, CMix is much, of course, simulation versus emulation. So simulation is much more precise. There are some limits for CMix. I had some problems running some code, but on the other side, the reference BIOS works quite well. There's also completely open source UEFI implementation for CMix for certain platforms. Then I really recommend it for running, and then you can introspect really up to the assembly, up to the even register states, what's going on. A very cool thing, and really recommend that. Other way is to use open source UEFI BIOS supported hardware. In this case, you can choose a platform which are available on GitHub in EDK2 platforms repository. It's a Tyano Core EDK2 dash platforms. And then you can check what kind of platforms are supported. There are some nice small platforms supported there, like Raspberry Pi, BeagleBoard. Everyone probably got one. If you're playing with embedded systems, you probably have one. And then you can use that code and use that hardware to really run it on hardware and play with UEFI Secure Boot. The last option I recommend and I really like, and this is what I professionally doing the most, is Core Boot and UEFI compatible payload for Core Boot or interface. So essentially, if you don't need something which is 100% compliant with UEFI and PA specification, you just need the interface, then you can use Core Boot, which is very minimalistic, simple, small replacement for your BIOS, and then use just the interface just to boot the operating system. Of course, it supports UEFI Secure Boot fully, so it's not like some simpler version. The difference is just for the initial bootstrap of the processor. It uses different code. It uses Core Boot code instead of EDK2 or some other EFI implementation. Yeah, and I guess that's mostly it. So if you like these topics, if you want to learn more about it, then feel free to join our training in Santa Clara.